The PRESS program is one phase of a cooperative US-Japan program on large-scale testing of structures for earthquake and wind resistance. This particular program, which involved cooperative research between Japan and the United States on different aspects of the seismic performance of precast concrete. The final phase is this large-scale test of a 5-story, what we call super assemblage rather than a building, to see how all the bits fit together and to make sure that when we test a real building that it does what we expect it to do.
The way we've done a lot of the design of this structure is to try to make the deformations, the places where the structure has to bend and yield, make those happen in the connections between the different pieces. Now, if you're building a cast-in-place concrete structure, then there are no kind of discrete connections between discrete pieces, and you don't really have that option. But with a precast structure, you can actually do that.
We are concentrating all of the inelastic action in the connections, which is quite different from the way in which precast concrete has been designed in the past, which has been emulating reinforced concrete, trying to make it exactly the same as reinforced concrete. We're not trying to do that. We're trying to make it quite different.
The question is, how can you have a building that after an earthquake is still occupiable? That's not what people are getting now when they buy buildings that meet code, and any engineer will tell you that. These systems that we're testing here actually go a step further, and they're trying to minimize structural damage in the event of an earthquake.
To prove these new systems, the project's research tool will be the largest structure ever tested in U.S. history. It is known as the PRESS Phase 3 5-story test structure, and it will be put through the final trial in a unique facility at the University of California's Jacobs School of Engineering.
The point of this structure is to try to pull together a lot of the individual connections which have been developed over the past 5 or 6 years and tested as individual connections over the past 5 or 6 years. And the intention here is to try to pull those together in a structure and then load the structure as if it really were being hit with an earthquake, to observe the way that the connections really work when you have them in a real structure and they're all tied together and all the pieces have to work together.
The structure will actually undergo 2 batteries of tests. In the north-south direction, 4 different frame systems consisting of columns and beams will be tested. The east-west direction will test a shear wall system. This wall system is a key example of the use of post-tensioning for seismic resistance.
In the east-west direction, the earthquake forces are carried by walls. They're precast individual wall panels, so you can think of it just like a gigantic playing card made of concrete. And they're held down to the ground by what we call post-tensioning tendons. And these are essentially enormous rubber bands made of very high-strength steel. So they're not made of rubber, but they behave like a rubber band. And so you put the wall down and you have a tube down through the wall, or a duct, and you stress this steel through the duct, and essentially that kind of clamps the wall down on the ground. But if you push it hard enough, instead of something breaking, it'll simply lift off on one side a little bit, so the wall will kind of rock over like that, and then the big steel tendon down the middle will just pull it back up straight again when the earthquake loading disappears.
The seismic frame systems will all be tested at the same time. The hybrid and pre-tensioned systems form the east side of the building, and the TCY and TCY gap connections form the west side of the structure. In the TCY gap system, there is a small gap between the end of the beam and the face of the column. The bottom portion of this gap is filled with grout to provide contact between the beam and the column. They are connected by 2 steel post-tensioning bars which run the entire length of the building, clamping the frame together. At the top of the beam, regular rebar extending the length of the beam and through the column is grouted in, except for a short length at the gap between the beam and column. When the beam moves laterally in an earthquake, the gaps at either ends of the beam open and close an equal amount, maintaining the dimensions of the frame system. Above the TCY gap connections on this side of the building, the TCY connections model a system that is similar to what is used in conventional cast-in-place construction. The TCY connection only uses rebar which is grouted in except for a short length at the beam-to-column interface. This connection is included since it emulates current use of precast beam connections. On the other side of the building, an innovative concept called unbonded pre-stressing is used.
Now, in previous pre-stressing of structures, normally the duct where the wire is passed through would then be grouted solid so that at all points along the length the tendon, that's the steel inside, is bonded to the structure, that's to the concrete. What tends to happen then is if you have a joint between, here's a beam on this side and a column here, as that joint opens up, it causes the pre-stressing tendon to gain a lot of strength and then go into the inelastic range. As it closes again, we lose some of the pre-stress. If the tendon is unbonded, we don't get that same increase in strength, but we don't get any non-linear behavior. We don't lose any of the pre-stress strength in the earthquake. And we've done a number of experiments which have proved this to be true on assemblages of beams and columns together, but this is the first time it's been put together in a total structural system.
Both the hybrid connection and the pre-tensioned beam, which form the east side of the building, use variants of Nigel Priestley's basic concept. The hybrid connections on the bottom 3 floors consist of beams which utilize unbonded post-tensioning strands that run the entire length of the building through a duct in the beams and columns. These strands are tensioned to clamp the frame together. Regular rebar at the top and bottom of the beam runs through the column and is grouted except for a short length at the end of the beam. When the beam moves laterally in an earthquake, the rebar yields dissipating energy, and the high-strength strands remain elastic, moving the frame back to center after the quake. Above the hybrid connections is the pre-tensioned beam system. It consists of long beams with pre-tensioning strands inside the beams, which are only bonded to the concrete at the ends. These beams are then set on one-story columns with reinforcing steel extending through the beams. As this frame displaces laterally, the unbonded strands remain elastic and recenter the structure after a seismic event. All these various systems have been carefully integrated into a structure that is designed at 2/3 scale so that it can fit in the huge Powell Testing Laboratory. Even though it is the largest lab of its kind in America, one of the challenges of the entire project is erecting the largest test structure ever built within the walls of this cavernous building. It was the charge of this man, Randy Clark, who directed a team of only 6 workers to erect the entire structure in merely 9 days.
We began the erection with the columns, and then we began to stabilize the structure by setting the beams along each floor at each elevation. And then we began setting the floor slabs. And the crew's done very well so far as to get every piece in with all the necessary parts.
The core objective of the testing is to study the structure's response to earthquakes. But how are the effects of a seismic event created inside a lab? Here at UCSD, the cadre of seismic design and testing experts has the ability to employ a technique called pseudo-dynamic testing to faithfully recreate the effects of an earthquake.
The reason that we can slow the earthquake down in this form of testing and still have valid results is because we ensure that the sequence of displacements that we put on to the building is the same as would happen to the structure if it was tested at a faster speed, in other words, at the correct loading rate for the earthquake. And damage is related to displacements rather than forces or anything else. So if we take it to the same displacements that would happen in the real earthquake and in the same sequence, then we get the correct levels of damage. In fact, we get slightly more because it's more severe on a building to hold it at the large displacements for a period of time than it is just to achieve it for a fraction of a second and take it off. So it's slightly conservative, but it is realistic.
The simulated seismic events for the pseudo-dynamic process are derived from a select variety of actual earthquake records, among them the 1940 El Centro earthquake record. These records are then modified to ensure that the structure is thoroughly subjected to the required levels of seismic intensity and beyond. The mechanical means which will bring the earthquake record back to life are the actuators.
For this particular test, we have 10 different actuators. We have 2 at each floor level. They come in different varieties with strokes from plus or minus 6 inches for the first floor, all the way up to plus or minus 24 inches for the top floor. The actuators on the first floor have a 165,000 pound load capacity. Those at the top floor have a 220,000 pound load capacity. This actuator here, for example, can push with a load of 165,000 pounds. That's something around the weight of like a 727 or a 737 jet aircraft. The actuators are kind of unusual in that we have this combination of really large forces, but yet we're able to control them down to very, very small displacements on the order of a thousandth of an inch. In the control room during the test, there'll be 5 of us. There'll be me. I'll be controlling the actuators and monitoring the health of the actuators and the data acquisition systems. There'll be Sri. He's monitoring what's actually going on during the test and conferring with Dr. Priestley to make decisions about what we're going to be doing next, whether the structure is behaving as we want it. There will also be 2 graduate students, Jim Conley and Stefano, and they will be doing close to real-time analysis of what's going on in the structure. The test actually takes place in several intermediate tests, and between those tests, these 2 graduate students spend a lot of time helping us make decisions about what we want to do on the structure next.
The structure is ready for testing. 12 years and countless hours of design and preparation have gone before. The testing begins. Time-lapse footage compresses the process. The team watches closely, monitoring the activity of the actuators as well as the response of the structure. A graphic display shows the amount of force the actuators are exerting to produce the target displacements. As it is subjected to the first loads, the structure makes evident its response to being displaced.
I think it's probably the pins, I guess, is it?
Something slipping in the pins, I think. Yeah. Okay, just hold it there for a minute.
The structure successfully withstands the design-level earthquake requirements.
We are right on.
Now it is crunch time. It will be taken to the extreme. The displacement will be equivalent to an earthquake which might occur once a millennia. The top floor of the building will move over 11 inches from center, or over 22 inches back and forth, much greater than the movement which occurred in